So today we're talking about the definite integral. This is where you actually are no longer using the plus c, okay? And the definite integral is basically the area underneath the curve, okay? So basically, whenever you're taking the antiderivative of a function, it's basically asking you to find a general equation to find the area underneath the curve, and that's what the definite integral is talking about. So the value a is known as the definite integral of f of x from a to b. It's written like so. So now, along your integral, it's going to be two values, and you're basically looking at that area underneath the curve and the x-axis from A to B. Okay? Now, some of these may be actual geometric shapes, and so your old school formulas of how to find, area of a triangle, or rectangle, circle, etc., will come into play here. And then we'll get to the ones that aren't so much geometrical shapes. Okay? Okay, here we go. So we'll start with the ones that are more general. Okay? It says evaluate the following integrals using area interpretations. And a lot of times it won't even say using area interpretations, but you'll have to recognize that we are looking at different shapes here. Okay? So the first one, we're looking from 0 to 3 of this function. We're looking from here to here, okay? And we're looking at the area underneath the curve. So we're looking at this piece right here. Now, what does that look like to you guys?
Trapezoid.
Like, so one trapezoid?
No, it looks like a pentagon.
Another trapezoid.
This is technically a pentagon, but within this pentagon, you can see how many trapezoids? You can see two trapezoids. You can maybe see
A rectangle, two triangles, and another rectangle.
yeah, like basically you can really break it down.
There's
Okay.
there's one, and then there's a rectangle, and then there's two triangles.
Yeah,
I see a
exactly.
butterfly.
But however you see, you
I see
basically
my
need
mother.
to find the area of those shapes and then add them together, and that will get you the integral from 0 to 3. Now, do you guys want to do two trapezoids, or you want to do two triangles, a rectangle, and a square? What do you want to do?
I say we do
Triangles,
one way.
rectangles,
Triangles, rectangles.
So, your first part will be this, the triangle, okay? What's the area of that triangle?
1.5.
1.5, yes, because normally it's 1/2 your base, which is 1, times your height, which is 3,
But also the side of C.
okay? Now you also have your rectangle, and the formula for a rectangle is base times height, so that's going to be 1 times 3, which is just 3. And then you have your triangle, which is 1/2 your base, which is 1, your height, which is 2. And lastly, you have your square, which is nothing but 1. For a total of
6.5.
6.5. So the area from 0 to 3 of your curve is 6.5. Okay? Then you also found that you did two trapezoids. Yeah. All right. Let's look at the next one. We're going from 3 to 7. 3 to 7. So that's starting here. I want you to find that area. You guys go ahead and do that. Go ahead and find the area of that figure. Can everybody see it?
I'm gonna guess 7.6.
You guys got it?
Yes, ma'am.
So you guys got that
Whoa,
one?
whoa, 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 whoa. Hold on. Hold it, Sam.
I am standing up and I'm walking through the board.
We're looking at that, right?
Oh, I'm still recording. All right, how'd you see it?
There's one triangle from like 3 to 4. There's a rectangle from 4 to 5.
Okay.
There's a little triangle right to the right of that below. It's like one square. And then there's the last rectangle, which is the rest of it.
Looks like the Power Rangers.
Okay. So what's the area of the triangle?
1 1/2 or 3 halves, I guess.
3 halves. And anything that's below the x-axis is going to be negative. So it would have been a negative 3 halves. What's the area of the rectangle? 3. Sorry, negative 3. And then
Other rectangle. 2. Was it
Negative 4.
it'd be a negative 4 for the square. And then the triangle,
Negative 1/2.
negative half. So what's that a total of?
Negative 9.
Oh my god.
Negative 9. Questions? Okay? Okay. Now from 0 to sorry, not 0. 4 to 2. Okay? From 4 to 2 you have this and this. Those two triangles, are they the same?
Yeah.
They are.
But one positive and negative.
Which means that
Zero.
it's gonna be 0. Good stuff, because it is literally the same. This triangle has an area of 3 halves. This one has an area of negative 3 halves. So yes, they do
How long
cancel.
would it have taken your studies to do that?
Shut up, Matthew.
You know some.
They can watch it if they want to watch it. That's Matthew Brooks, trademark.
All right. Now for the last part, from 0 to 7. From 0 to 7, so it's the whole thing, the whole area.
Oh no.
Okay? Now technically,
That's 2.
from 0 to 7 is nothing but from 0 to 3
And then
3 to 2.5.
plus 3 to 7. So you basically just add those two values together. So 6.5 plus a negative 9, which is what? And that's the area underneath your curve. Yes? It's negative. And that is fine. Questions? I want you to do this next one. Oh, just kidding. These are your properties of definite integrals. Okay, so a couple things you need to know. If they ask you to find the integral from A to A, clearly that's 0. You're not traveling anywhere underneath the curve. Alright? They ask you to find the integral of a constant from A to B. Okay, well that's nothing but the constant times B minus A. If you go from B to A, you just negate it. And it flips the bounds. A to B. Of course you have your constant. You just pull that out. That last example is the second to last one of the integral from A to B of the function plus the integral from B to C is basically the integral from A to C. And of course you have your addition rules which applies. If I recall, none of these are in the reference book, okay? They pretty much are straightforward. Alright, so applying these properties, I want you guys to take a look at these two. Okay, these are two separate. These are two separate problems. Okay, you have the integral from 1 to 3. Why should I do the first one too? Now, see, that's the same one on your own. The first one, it says from 1 to 3 of the function, the integral is 2, and then from 1 to 6 of the function, the integral is -3. You have to find from 3 to 6. Okay, so basically you have part of it, you have the whole thing, and it's asking for that part in between. Okay? So visually, it's kind of like this. You have 1, 3, and then 6. Just making up a curve. Okay? So 1 to 3, you know that this area is 2. But then from 1 to 6, that area is -3. And I know this doesn't represent it accurately, but follow me here.
So you gotta find the last box.
You're trying to find this last box right here. You're trying to find this space right here.
So you
2 plus what is going to give you negative 3?
Negative 5.
So, the integral. Negative 5.
So I didn't have to write this all out for you?
Okay? And if you can't quite see that, then just set an equation. 2 plus x equals negative 3. Just solve x equals negative 5. Okay? But you guys to try the bottom one. Do this one on your whiteboard. This is 4. Okay? You want to think of it? Okay? You know that from 0 to 2, you have an area of 5. Okay? And then from 4 to 6, you have a negative 2. So you're basically trying to figure out this middle part here because you know the whole thing is positive 7. And so yes, your answer would have to be 4. Questions?
So Brian has a question. Now we'll see.
Alright? I want you guys to do A, B, and C. Save D for me. Unless you think you can do it.
I can do it.
Alright, if you think you can do it, then do it, but definitely try to do A, B, and C.
Brian can't do it.
What in the world? Like, why?
We're gonna see if you can watch it. We're gonna see.
And Manny can't either.
Alright, so checking your whiteboards real quick. If you notice, A is an example of that property that basically the bounds are switched. So for A,
Flip the sign.
if you just make it negative, it flips the bounds. So all you really are doing is just negative, negative 4, which is a positive 4. Did you guys get that?
Yes.
Good stuff. Now for B, it's 2 plus that, okay? Now if you think about it, that you have your function plus 2. You think back to the very first unit, whenever you have a plus 2 being added to your original function,
It shifts it.
it shifts it up. So technically, from negative 1 to 1, you basically have this function here. But when you have a plus 2, that's basically taking that function and moving it up 2 units. Okay?
Yeah, we couldn't solve that one then. Do you move or do you go up?
Well, see, the thing is,
Honestly, this part really doesn't matter. Okay? Because you already know that this area is a negative 4, and I know this is not accurate representation, so just bear with me. Alright? So, you already know that that area underneath the curve was a negative 4, but because you went up 2 units, it basically created a box underneath. Like literally that curve just went up 2 units, creating this extra space underneath the original curve. This is a nice little rectangle or square. It's a 2 by 2. So you're basically adding an additional 4 units for a total of 0. Okay?
But then, how would the negative 4 stay negative 4 if it's moving up?
Because technically, I guess my drawing should have been more like this. So, 1, it technically was like this. So then that way, when it moved up, there was no area. So it's just,
what if part of the curve is up and part is down?
you still have that additional area underneath it. Once I go over the fundamental theorem of calculus, we need to read this problem we tried that.
Okay.
For C, what you guys do? Multiply, remove the constant. So then that's nothing but 2 times negative 4, which is negative 8. And then for the last one, did anybody do the last one?
Yes.
Okay, so that is nothing but a constant, so you can pull that out. All that equals 7, so technically you have a 4k, a negative 4k equal to 7, so k was a negative 7/4.
Yes.
Okay? So you can apply your properties to even these types of general problems.
Why do you want us to wait on that?
Well, I didn't want to. But looks like you guys get
Well, Brian and Manny, not us.
questions. All right. Now, the fundamental theorem of calculus, when we actually know what the function is, we can apply the definite integral using this theorem, which basically says that antiderivative, plug in the top bound and subtract it from when we plug in the bottom bound. So we still take the antiderivative as normal, but we actually are getting a value when we plug in B and subtract it when we plug in A. So these are for your more explicit functions, okay? When you're actually given like x squared or, you know, x squared plus 4 over 3x minus 2, right? So we're going to look at some examples that apply the fundamental theorem of calculus. All right, this first one, I'll do this one with you. After that, hopefully you guys get the idea. Well, just refresh your memory on the idea. So we just take the antiderivative as normal. What's the antiderivative of 2x?
2. Oh, x squared.
It's going to be x squared. Okay? Say that's a constant. And then that'll just be 1/2 x squared. It's just x squared. But since we actually have bounds here, this is where we evaluate x squared from 1 to 0. So basically we're looking at the old school quadratic function, and we're looking from 0 to 1. We're looking at this area underneath the curve. This is basically what the whole concept is with an applied function. You're trying to figure out what's this area here from 0 to 1. So to do that, you take the antiderivative, and then you plug in your top bound, which is 1, and subtract it when you plug in your bottom bound, which is 0. 1 squared is 0 squared is, and 1 minus 0 is 1. So that means the area underneath this particular curve is 1. Alright? This one. Whiteboard. Make sure you take the antiderivative first. There's no plus C's whenever you're doing ones with bounds. Then you plug in B, your top bound. You plug in A, and then you subtract those two values. So you're doing that on your whiteboard. Seriously, guys.
Negative 7.2.
It should be a negative 36 over 5, which is a negative 7.2, okay? So you take the antiderivative. What's the antiderivative of x to the third? X to the 1/3.
3/4 x to the 4/3.
And then, what about the 2, x to the 2/3?
Negative 3/5 x to the 5/3.
So then you evaluate that from 0 to 8. Now realize, of course, that anything with an exponent can be written as a root. I think you guys were good. I'm just doing this one. And then you plug in 8. You plug it into both of them. And then you also plug in 0. But when you plug in 0, what's the cube root of a 0?
0.
It's just 0. Okay?
Yeah, Brian, you should have known that.
Seriously? And so then you could just get 12 minus, what was this number, 96 over?
Or 19.2.
So then it would be a negative 36 over 5. Okay? Clear your boards. Here's another one. Yes, ew. This is 16 over 3 because you need to make sure that you FOIL and then take the antiderivative from there. So your final answer should have been 16 over 3. Here's your next one.
5 1/3.
Okay? Actually, before we do this one, I want to revisit
The BC minus BA.
this one over here, okay? With B. So another way you could actually tackle that problem, it was 2 plus f of x dx, okay? What you could do is you could separate them. You could always separate them. You already know that this part here was a negative 4. So then all you have to do is take the antiderivative of 2, which is 2x, and then evaluate that from negative 1 to 1. Now realize that you always plug in the top bound, which is 1,
You subtract the bottom bound.
and subtract the bottom out. So when you plug in 1, you get
2.
two
Minus
Negative 2.
minus a negative 2. 2 minus a negative 2 is
4, Brian.
a positive 4. So when you add that to a negative 4, you get 0. That's why n to be 0.
Negative.
So now with that being said, no more shots thrown. You guys are doing this one on your whiteboard. This one is nothing but pulling out the constant. So there'll be 3 times 8, which is 24 for A.
10.6 for B.
And then for B, just separate them.
No, ma'am.
So this is 8 plus, you do the integral and you evaluate it from 0 to 2. So that's 1/3 times 8 minus 1/3 times 0. So then it'll be 8 plus 8/3, and that's how you get 16.
Okay. We're supposed to know our squares all the way up to 25. You just asked it if we could use a calculator.
Wait,
Like how?
you just wrote 16.
What is it supposed to be?
32.
32, I'm sorry.
That was the last answer.
That was the last answer. 32. Alright, whiteboards. We're whiteboarding it for the rest of the time, okay? That is an LN6.
Yeah.
K is 12, because when you take the antiderivative, it's ln of x, you're evaluating that from 2 to k. And realize that ln is equal to 6. So when you plug it in, you guys are going to have to remember some old school properties of ln. Okay, if you wanted to, you could have added, and I think a lot of you guys did this, you added ln of 2 to the other side. And remember, whenever you have logs and you're adding, they turn into multiplication. So the ln of 12 equals the ln of k. If you have 2 ln's or 2 logs that equal each other on both sides, they just drop, and k equals 12.
You want to see our work? What do you need?
Clear your board.
What do you need?
Here's the next one.
Is that a pi over 3?
I know it's a little blurry. It was better than smaller than this.
Okay, now I know what it says.
You have negative pi over 3 to pi over 3 cosine x ds. Okay, the antiderivative of cosine is
We're an idiot.
positive sine.
And cosine.
Idiot.
So you're going to plug in pi over 3 and subtract it from when you plug in negative pi over 3. Sine is the x or y value on the unit
The
circle.
y value.
It's the y value on the unit circle. So and pi over 3 is actually root 3 over 2. And then this one is technically in the 4th quadrant here, which is a negative. Okay? So, 2 negatives make a positive. So when you add them together,
2 root 3 over 2,
which is just root 3.
That's what I had. It just looked like a 1.
I got that. Matthew has.
Yeah, if Matthew was better at math, I wouldn't have failed.
You know it's true though. Crazy.
Like Laura.
Here's the next one. Alright, all different boards. Just gonna look at this one as a group. This one does involve the 1 over a sine ax plus b. So you should have had 3 over 2 sine 2 over 3x and evaluating that from 0 to pi over 2. Did anybody have that? That's the antiderivative. So then when you go to plug in, you would have had 3 over 2 sine, when you plug in pi over 2, that just turns to a pi over 3, minus 3 over 2 sine of 0. You do need to put 0 because if it was cosine, it would definitely be something. But what's the sine of 0? 0. So that's actually gone. So then we have 3 over 2. What's the sine of pi over 3? So then when you multiply them together, you get 3 square root of 3 over 4. Questions on this? So I need to revisit your unit circle. Here's the next one. You guys see this one okay? This is a pi at the top.
Yeah, that's fine.
Be nasty.
No.
Should be positive 4. So it turns to a 2. Sorry, negative 2 cosine x when you take the antiderivative. And then minus a 1/2 cosine 2x that you evaluate from 0 to pi. Please be careful when you're going to plug this in. When there's multiple terms, please include a parenthesis, so then that way you know that you're subtracting the entire lower bound. Okay, what's the cosine of pi?
-1.
What's the cosine of 2 pi?
1.
What's the cosine of 0?
1.
And the cosine of 0, which is 1. Okay? That's how you end up with positive 2 minus a half plus a 2 plus a 1/2, and the 1/2 cancel out, leaving you with just a positive 4. Okay? Now, some of you guys end up lucking out because you mess up on your signs, you might mess up on your trig functions, and you still end up with 4.
Or you don't know how to
Okay, shut up. Yes.
Where did you get that 1/2 for the cosine 2x?
and right?
Because that's the one, remember when sine ax plus b, you take the integral, that's equal to a negative 1 over a cosine ax plus b.
Oh, okay.
That's one of those special ones. Stop the clicking. Let's do, I know some of these are kind of hard to, stop it!
That one doesn't like you.
That one. I want to do that one.
Let's do this one.
That one looks fun.
Okay, let's do this one. Remember, you take the antiderivative, so 1 over negative 2, 1 over a, 1 over n plus 1. You're evaluating that from negative 1 to 2. When you plugged it in, yes, they canceled out for a big old loose egg of a 0. Let's do 2 more. Let's do this
I
one.
like that one. I like that one.
I don't like it. In fact, I hate it.
One thing you should eventually, you just write the answer. Like write the question as the answer.
What is?
Like take that and write it down. And say that's your answer.
Working. But I want to show you guys a couple of things, okay? With this one, you can kind of do this one of 2 ways. Of course, you would need U substitution for both of them. Hopefully you made the bottom U, which meant that when you took the derivative, you got 4t minus 3, but you needed to do what to it? Multiply it by 2. That's how you get 8t minus 6 dt. So when you go to plug it back in, you have du over u with the 2, which is just the same thing as saying 2 over u du. Then you'll have 2 ln of u plus c, but we actually have bounds here. Before we actually can evaluate the bounds, we have to plug back in, okay? So you would have had 2 ln of this whole expression, evaluating that from 3 to 4, okay? Now when you plug in 4, you would have ln of 18 minus, what do you get when you plug in 3?
7.
Huh?
7.
7. Now whenever you're subtracting, you are going to end up dividing. And that 2 is your constant, so technically when you plug in your bounds, that 2 is on the outside of that ln 18 over 7. Now, another way you could do it, still using U substitution, so you still would have had to do these 2 steps, okay? But what you could actually do is, when you get down to this part of the 2 ln u, you can actually evaluate it with different bounds, okay? So those bounds are originally from 3 to 4. Since we're using U substitution anyway, what you can do is actually plug 4 in and plug 3 in to get new bounds, okay? So if I were to plug in 4 into this equation right over here, what do you get? Plug in 4, what do you get? Say again? No.
18.
You get 18.
Yeah, we saw.
Sorry, I thought I heard, but I was like, wait, what? What do you get when you plug in 3?
7.
You get 7, okay? So you could change the bounds, that way you don't ever have to worry about plugging back in. So then that way, when you do, you'll have ln of 18 minus the ln of 7, which takes you right back to this step there.
Which gives you 4 to the half log.
Anyway, so So just remember, if you don't change your bounds, you have to evaluate it once you plug U back in, or you can change your bounds by plugging in the old bounds into your U equation. Does everybody understand that?
Yeah.
It's just another way to do it.
Yeah.
Okay.
Yeah.